So I'm happy to introduce Jan Pulmann from University of Geneva, who will talk about quantized modular spaces of flat connections and triangulations.
Oh, thank you very much. And also thank you very much for giving me this slot and also for organizing such a nice conference. And I will be talking about, what will hopefully be my thesis. And this is done under the watchful eye of Pavel Ševera. So the title is Quantized Modular Spaces of Flat Connections and Triangulations. So the first part is old story, this quantized modular spaces of flat connections, and this triangulation that is the new addition. And the kind of modular spaces we consider are modular spaces of flat G connections for a Lie group G on surfaces. So this is the setup, and you probably know that such structures are abundant and they have there are many important examples of them. Partly because these modular spaces of flat connections on surfaces, they are symplectic or Poisson or something I will use, a quasi-Poisson manifolds, or if they are manifolds, then they are Poisson manifolds. This is the famous Atiyah-Bolt structure, symplectic structure, and generalizations of that. And sorry, I wanted to see all of you. And there is a natural question to how to quantize these structures. And this was done by Pavel Ševera and David LeBlanc. And they have a procedure that gives you algebras that quantize these Poisson structures, but they are algebras in some kind of bit different category, which you craft using the Drinfeld associator. And the question in this procedure, it involves cutting up the surface into small parts and then gluing it back together. And there are lots of choices you can make while cutting up the surface. And this is the answer we will provide is how does the quantization depend on these choices? Okay. And I will try to give you all the necessary background to follow. So first, let me just talk about modular spaces of flat connections. So for me, G is just a connected Lie group, and sigma will be a surface with a non-empty boundary. I will always consider non-empty boundaries. And then one can look at this space I will call M sigma of G. Okay, and this is the space of all flat connections on the trivial bundle on G. So because the surface has non-trivial boundary, all the principal bundles are trivial. So at least So we look at just flat connections on this trivial bundle, and we take them up to gauge transformations. So gauge transformations, these are here we can just see them as functions from the surface to the group. And if you have a connection, there's a Lie algebra valued one form on sigma, you can change it by this small formula here. Okay. And there is an equivalent description of this space, which I think when people say character variety, they rather mean this one, but these two are the same. And so this other description is just, you look at homomorphisms, or group homomorphisms from the fundamental group of the surface to your group G. You choose a base point, and then you mod out by G. So let me maybe write how does the G act. So if you have a homomorphism phi gamma, then if you act on this homomorphism by G, what you get is phi gamma and it's conjugated. So the action is simultaneous conjugation by all the simultaneous conjugation of all the maps. So Nikita has But I think here this is the smooth category, and so okay. And this isomorphism between these two pictures is very easy. You just, for any flat connection A, you can take holonomy along path. And because we only look at gauge transformation at flat connections up to gauge transformations. Sorry, then this holonomy is only defined up to conjugation at this marked point, right? Because there is still, you can still use some gauge transformation. Okay, and what I will consider is a slight update of this, which contains the previous situation. And what I do is I choose few marked points on the surface, on the boundary of the surface. So this is the set V. It's a finite set of so-called marked points. And so what does this mean? Like, yeah, one can just draw points, but for the flat connections, it means that we restrict those gauge transformations to be equal to the identity at those marked points. So one thing you immediately see is that the holonomy is now well defined. It's not defined up to conjugation because there are no gauge transformations if you take the holonomy along a path which ends at those marked points. Okay, and this is written here in green at the bottom, that this equivalent description is we look at homomorphisms from the fundamental groupoid with objects, those marked points, to the group. Or that is to say, this moduli space is just an assignment of a group element to each path between those marked points up, and the paths are taken up to homotopy because the connections are flat. And you can always just go back to the previous picture, because this space, it has a G action for each marked point. Yeah, this is the gauge action we forbid, so it remains as an action. And if you just take the quotient, we recover the previous space. Yeah. And why do people use this space? Is because now it's really a manifold. It's isomorphic to a product of the groups, and it's nicer to work with. And at the end, you can quotient and go back to the usual case. So let me give you an example. It's very simple-minded. So we just look at a one punctured torus. So this is the torus. There is this one puncture, so there's a hole. And to get an explicit description of the moduli space on this torus, one needs to do some choices. So there is a non-canonical description, and the choices you have to choose some paths that generate the fundamental group, right? Because if the surface has a boundary, this fundamental group here is free, so you just need to specify the value of this morphism on generators. So here one can choose generators like this, A and B. And in the case where we consider the marked point, we just get that the moduli space is given just by a pair of two elements of the group, the holonomies along A and B. And there is an action which looks like this. So yeah, this is conjugation, which corresponds to the gauge transformation, to the gauge action here. And if we don't want to see it as a surface with marked points, just as a surface with boundary, then the moduli space is G cross G modulo this action, right? Exactly this action. Okay. So let me talk a bit about the Poisson structures on these moduli spaces. This goes back to, as I said, Attia, Bott, and then Goldman. So one needs to fix a non-degenerate invariant symmetric pairing on G. Yeah, I should maybe write that G is the Lie algebra of our connected Lie group G. You should think of a Killing form. And then there is a canonical Poisson structure on this moduli space. Yeah, which was given by Attia and Bott for surfaces without boundary, and there is symplectic, and then, but actually, if you have a surface with boundary, you get just a Poisson structure. And there is a slight generalization one can do, and it's not necessarily to have a non-degenerate invariant pairing, because what one uses in the construction is actually the inverse of this pairing. So it's enough to take just an element of this space, so of the second symmetric power of G, but invariant. So, and if this thing is non-degenerate, you can just invert it and get the pairing, but you can also take a non-invertible element here. Yeah, for example, 0, and then the Poisson structure is 0. That's a very stupid example. So what comes now is the generalization for these moduli spaces with marked points. So remember, if we have these marked points here, this has an action of G, of V copies of G, or let's look at this also the Lie algebra action. And then this space is canonically something that's called quasi-Poisson manifold, and there is this action that we have on this space. This is due to Anton Alexev and Yvette Kosman, Schwarzbach, and Eckhart Meirenken. And let me just give you a definition. What's a G quasi-Poisson structure? So it's a G manifold M. So here, this is our moduli space. This is the group, or multiple copies of the group. And there's an invariant bivector pi, such that it's not a Poisson bivector, but the Schouten bracket with itself, which should be 0 for usual Poisson structures. It's this thing phi m. We actually saw this thing in the first talk by Leonid Rivkin. This is called the Cartan trivector or Cartan element. This is because this equation, this holds in the would you define the invariant? Okay, maybe I will reach it. I don't know. So it's a manifold with a G action. So you want the bivector to be invariant under this G action. Okay, sorry. So, and in this equation, I need to tell you what this trivector is, and it's the G action of the trivector phi, which you have in the third wedge. So, okay, so once again, if you have the Lie algebra with this non-degenerate pairing, you can define an element in third wedge of G. This is the element we saw in the first talk. In coordinates, you can just lower the indices of the structure constant, and this is totally anti-symmetric. And then if you have a trivector here, you can act on it to get a trivector on the manifold. So one just gets one has this constraint. And now if you look at the quotient space of this manifold by this group action, the bivector descends onto the quotient, but this right-hand side here, this is if you just acts on invariant functions, it acts by 0 because the functions are invariant. So on the quotient, you get really a Poisson structure, and this is the Attia-Bott Poisson structure. So this way, this quasi-Poisson setting, it encompasses the usual Poisson setting. Okay, and there's a natural question, how to quantize these things. So first, what to quantize these things, right? Maybe let me recall that if you have for Poisson manifolds, what one does, one has this C infinity of M and a Poisson bracket, and one looks at an algebra A, which should be, let's say, C infinity of M and power series in H bar, and a star product, such that the 0th order of the star product is the usual commutative multiplication, and the first order of the star product is anti-symmetrized gives you the Poisson bracket. And because the product is associative, one gets that the Poisson bracket will satisfy Jacobi identity. Okay. The situation we have here, we have this, let's say, these functions on the moduli space. It's a module under, I will use the language, it's a module under the universal enveloping algebra of V copies of G, right? And it has a bracket, but it's not a Poisson bracket because it's a quasi-Poisson bracket. And what it means is that if you look at the Jacobiator, this expression, you don't get 0, but something, you get phi evaluated on these three differentials. So what the quantization should be, so one can try to do the same thing. It should be just power series with some star product, but it cannot be associative in the usual sense, because then the first order commutator would be Poisson. So this was first realized by Enriquez and Ettinghoff. The correct notion is an algebra in a slightly different category, and the category is this Drinfeld category. So you take it modules for this UG power UG to V, right? So these are just like, as a category, these are just modules for this universal enveloping algebra or G power V representations. But first, there is this little h bar. This just says that morphisms are power series in the usual morphisms of modules. But what you do, you change the associativity constraint of your category. And because this associativity constraint that comes into the equation for the associativity, and this element which changes the associativity is called Drinfeld associator. It exactly contains this phi. Then you get that the first order commutator of an associative multiplication in this category is a quasi-Poisson bracket. Okay, so just to recapitulate, a natural notion of a quantization of these quasi-Poisson algebras is an algebra in this category. It's an associative algebra in this category, which is a braided monoidal category. I will talk a little bit about it in the parallel session. Okay. So now really to quantize, I will very briefly describe procedure by David Leblanc and Pavel Chevera, but I should mention that there were other works, maybe Alexei Grosset-Chomerus and Roche-Senesh, which were quantizing just the Poisson structure on the flat connections, and also there is this approach by factorization homology by Brochet and Swijordan. But let me go back to this procedure of David Leblanc and my advisor. So you can use, what you do, you have this category of UG modules. Sorry, there should be this phi and h bar. And you use in some way this associator phi and the tensor product you have here to in the following algorithm. So first, there is just one thing one needs to do. One is to decorate each marked point by either plus or minus. This is not very important, but you don't see it at the Poisson level structure, but at the quantum level you see it. But it's possible to just pass from plus minus. So I will not dwell too much on this point. And then what you need to do, you need to glue your surface from these following basic blocks. So the procedure basically says that for such block, there is a very easy algebra that quantizes the Poisson structure. Actually, the Poisson structure is it's actually Poisson, and just the functions on the group quantize the Poisson structure here. And sorry, you just have this building block, and then what you need to do, you need to glue the surface from these small building blocks, and you have two allowed moves. Either if you have 2 points with the same sign, you can connect them like this. these can be either on the same side of the surface or on the same component of the surface or two different components of the surface, right? So you can, for example, either you can glue disks to bigger disk, or you can have one component and then add basically genus to the surface. Anton is asking whether these building blocks are commutative. Yeah, that's what. Yeah, they are commutative in the twin-file category. And another move you are allowed to do is to forget a point. This is easier, and it just corresponds to quotienting out by the action at that point. Okay, but it looks like there are lots of choices you can do while gluing the surface. So this is a question: how does this category A depend on this gluing? And sorry. And after we make some modifications of this Leblanc-Chevra procedure, then one arrives at the following. So the theorem says that the choices you need to make are a graph gamma. It's an embedded graph, and it has two kinds of vertices. Okay, so it will have univalent vertices, which are mapped bijectively to the marked points, and then trivalent vertices, which are mapped to the interior of sigma. So there are two examples. Maybe I'll make them a bit bigger. Right, here you have just a disk with 4 marked points, and this is one possibility. You can also imagine the other possibility, right? Which would look like this. And for example, for this one punctured torus, you can do something like this. So the vertices in the interior, they have to be trivalent, so you cannot just draw the usual skeleton as one would do. Okay, and because there is an important condition that sigma should deformation retract to the graph gamma, right? And here you see that it's the case in all these examples. Okay, and if you have this structure, then what we get is an algebra in this twin-file category. This is A gamma in UG power V mod phi. So it's an associative algebra in this category. So it has this star product, which it will quantize the Poisson structure. We want to quantize the quasi-Poisson structure in quantize. But not just this, we actually know very well how this structure depends on these graphs. And there's a following simple claim that any two such graphs are connected by sequence of this following simple moves. They are called flips or sometimes wide-head moves. And now, what I claim is that if two of these graphs are related by such a move, then there is an explicit isomorphism between these two algebras. And not just that, but this isomorphism is actually compatible with the relations among flips. Because it can happen that if you do many flips, you end up in the same graph. And the claim is that the composition of all these isomorphisms is identity at the end. So one can say that this functor, which gives you the algebras, is a functor from the Ptolemaic groupoid of sigma, which is just the groupoid where objects are just these graphs. Anton is asking what about the mapping class group action. Yes, then the mapping class group acts on this algebra. If you choose one graph and then then you choose an element of the mapping class group, it changes it to a different graph, and you can go back. This gives you an element of the mapping class group, which relates slightly to the following. Yeah, I am writing it here, and it's related slightly to a slightly more general claim that if you embed a surface to a bigger surface, then the embedding is compatible with the with a graph, then you get an algebra morphism in the same direction. Yeah, there are two duals, so you get a morphism in the same direction. If I have 20 seconds, there's one thing I want to say, because in the abstract I talk about triangulations, and here I'm not talking about triangulations, but I'm actually talking about the dual thing, the graph. And that's because, for example, the triangulations can be somewhat singular, because, for example, this is a really nice graph, but seeing this as a triangulation of the disk with 2 marked points it's like this. It's not very nice. Okay, so I thank you for your attention, and you can see what I plan to do in the parallel session.
Okay, thank you very much, Jan. Let's thank Jan with emojis. As if anyone has read my introduction on Slack, you know that I love emojis, so I particularly appreciate the clapping emojis. I hope, Jan, you are like-minded. But anyway, so I'll use my privilege of the microphone on.